Okay, this lesson we're going to start looking at our last chapter for the course, and we're going to look at what a cloud and bubble chamber is and what it does. The idea up till now, we've identified electrons and their charge, and protons and neutrons, and all these different particles within an atom. The question is, we know what they should do in a magnetic field and an electric field, but how do we actually see that it does that? How do we actually prove that it's indeed true? So this is where the cloud and bubble chambers come in. So the idea is, how can we reach around in the dark or be able to find these things or be able to see these things in areas that we actually can't see? So physicists got the idea from Charles Wilson, and he was using cloud chambers to try to mimic what happens in clouds in terms of weather patterns. So he basically would make a mini cloud in a glass chamber, and he realized that if there was charged particles in there, they would ionize some of the water vapor, and you'd see these little vapor trails behind the particle. So it's kind of like when you see an airplane go through the sky, same sort of idea. So what physicists did then is they basically tried to copy the same idea. They would make a cloud chamber, move a charged particle through it, and they'd be able to see the trail it left behind. A bubble chamber now is pretty much exactly the opposite. So instead of having water vapor inside that we try to disturb or change, the idea is we put a supersaturated liquid in there, so we have some sort of gas that's already at basically boiling points. We're ready to have this liquid boil, but not quite. Then we shoot a charged particle into the liquid, and the friction that it causes as it goes through it actually boils the particles that it touches, and it basically leaves a little bubble chamber. So they both kind of do the same thing. One is sort of leaves this little trail of kind of smoke in the clouds. The other one basically leaves a trail of bubbles. The idea behind both of them, though, is we can actually see what's going on. So you can see in this diagram at the top, a charged particle was actually shot in, and you can see it sort of makes a curve and leaves a little trail of bubbles behind. So because we know which direction magnetic fields are in and things like that, we can then figure out which direction things are curving due to the magnetic force, what the radius is, what the speeds would be, charge to mass ratio, and we can also see which way they would actually spin. So in terms of things orbiting, they actually spin as they go in this. We can kind of measure that as well. The biggest drawback from both cloud and bubble chambers is it's pretty tough to detect a neutral particle. So if you have something neutral there, it's either just going to go straight through, which is pretty tough to see. So in terms of a cloud chamber, you wouldn't be able to see neutrons. In terms of a bubble chamber, the friction and the energy that it passes would still leave a little bit of bubbles behind, which is typically why we kind of use bubble chambers more so. So the best way to get these things to work basically is put the chambers in a magnetic field, and then we just basically allow these things to curl. So we have Fm equals Fc. So if we look at this first example, we know our magnetic force is QVB. We know our circular force is mv squared over r. And we can actually figure out charge to mass particles. So if we go charge to mass, that is V over Br. So if we do that for this question, they give us the velocity of the particles. So they tell us that it's moving at 0.2024 times 3 times 10 to the 8th. And we know our B they give us in the question is 4.75 to the negative 3. And we know the radius is 8.55 to the negative 3. So if we actually do that calculation, we can see that the charge to mass ratio is 1.77 to the negative 11. And if we compare that to an electron, so if we do charge to mass, we just do basic charge, elementary charge. So 1.6 to negative 19, and we divide that by the mass of an electron. We do that calculation, we see that we get pretty much the same answer. So the first one was 1.77, this one works out to about 1.76, but we see that we get pretty much the exact same thing. So when you do these, oh sorry, it was positive 11, not negative 11 for both. So, but we can see that the charge to mass ratio works out to be the same. So based on just a simple example like this, we can see, okay, well, we know these particles are curving, they're going in opposite directions, and it works out that the charged particles are pretty much the charge to mass ratio of an electron. So if these two things were shot in from the left, we then know one has to be positive and one has to be negative, so we know one's electron and one's a positron. But if we know that the magnetic field is coming out of the page, we can use our third left-hand rules. So if we put our thumb to the right, point your magnetic field out of the page, you can see that the force would go upwards. So for our left hand, our force goes upwards, so this one would be the electron, and if we use our right hand, it would be the opposite, so we'd know that the bottom one is the positron. And that's it. So you can see the idea with bubble chambers and cloud chambers. The idea is to basically, first of all, see the particles as they react in the magnetic field, and then use things like the size of the ratio of the curves and which direction they're going. We'll be able to determine whether it's positive or negative and whether it's a bigger particle or not. So for example, if we were to, let's suppose for the same diagram, if we were to shoot a positive particle in, like a proton, we know that it's going to curve downwards, but because the proton's mass is way bigger, the radius would end up being way bigger as well, so we'd see it'd be a curve, something like that, not just a tight spiral. The radius would end up being much larger. And that's all.